Awesome. Thank you, everyone. Very, very happy to be speaking here. Before we get started, could we all just kind of maybe stand up, stretch? I know it's been a long day, and it's good to get the blood flowing. Maybe one of those weird ones where you use your brain. I know we've probably done a little too much of that today, but maybe we can keep it going. So yeah, my name is Thomas Omans. I am an engineering lead. I go by Exby at the internet, and I blog sometimes at Samesake. I work at a company called Junction. We're in the affiliate ad space. We're a pretty large company, but we're a very old company. And I'll talk a little bit more about that later, but first it's just great to meet everyone, and again, thank you for coming. So why am I here? I want to talk to you guys about a library called Kafka-Rx. And what this library is just a high-level wrapper around the producers and consumers that ship out of the box with Kafka. Here's an example of some of the code that you might write with a system like this. So here we have a tweet stream, presumably living in Kafka. And at this state, we're assuming it's kind of raw data. It's just a stream of tweets. However it got there is not really the concern of this program. But what we do want to do is we want to look at it and we want to group it by this hashtag function that's going to look at the tweet and extract some information about it. So this is really cool because you guys have probably seen these group by and these flat map functions in Scala collections if you've been doing that style of programming. But here we're doing it over this asynchronous event stream. So when we group them by their hashtag, now we have substreams. And we're able to process those substreams independently and still in this asynchronous context. Something that we found was really cool is that if we could get a stream of producer records, these things that come with Kafka that you say this is how you get a message into the system, then now we can stream them into Kafka if you just hand it a producer. We used implicits to get this behavior, and we just attached it to the API of the Observable. Also, we wanted very specific commit semantics. And so here we're actually calling message.commit, but it might be a little weird because it's actually coming from the result of saving to Kafka. And this commit is committing back in the original source stream of tweets. So we've had a whole transformation that's been going on, but we're keeping track of where we were. This is very similar to storm checkpointing. So why did we write Kafka-Rx? There's a lot of stuff out there, and I'm sure many of the people here are familiar with the Kafka story, are familiar with the data integration problem, the legacy systems problem. And as it turns out, Kafka is an amazing way to separate your systems from one another. You can use it to rather than two discrete components of your system knowing the intimate details of one another, unfortunately, they know the intimate details of Kafka instead. This is a trade-off we think is worth it, but it is absolutely a trade-off. So Rx is a library for stream transformations, and Kafka is a system for streams. So to us, this seemed like a natural mapping. The existing clients didn't support the sort of things we wanted to do. We wanted to peek into the stream, and the Kafka client just didn't support that. It could, but it just wasn't what people were using it for before. And so because of this, we're here today. CJ is, like I mentioned, a very old company, and that means we experienced a lot of time. Some things grow with time, like data, for example, accumulates with time. The longer that you're running a data system, the more data you're going to come in, the more data you're going to be able to process. Unfortunately, the longer your system is around, you're going to get this other really strange thing called technical debt. And what this means is that you make architectural or infrastructural decisions, and they start to crystallize into your applications. And it makes it very, very hard to change your applications. And it's very strange because these two things are completely at odds. On one sense, data loves to change. Data loves to evolve. As new requirements are added or removed, we're continuously changing our schemas. We use Avro for this. And debt, on the other hand, makes it impossible to do exactly those sort of changes that you need to do if you want to continue moving. So how do we reconcile these things? We know that our problems are changing, and they're changing faster than our tools. So how can we keep up? I think it's pretty simple. All you have to do is find the simplest solution that solves your problem and then use it. Rich Hickey stated this very eloquently in a talk called Simple Made Easy. If you haven't seen it, I recommend you go watch it as soon as possible. But the general idea is that you should battle complexity. You should not accommodate it. You shouldn't have very complex systems, but have ways of dealing with that complexity. Instead, what you should try to do is you should weed it out at the root. So what sort of stuff am I going to be talking about today? Primarily, one thing, streams. Streams. In order to talk about that, I think we're going to have to go over some terms and definitions, because I think stream processing is one of those things that means a lot of different things to a lot of different people, and I just want to make sure that I clearly let you guys know what I mean when I say these words. After that, we'll get to a little more theoretical stuff, what the problems in stream processing systems are, and finally we'll get to the practical usage. So what is stream processing? I define stream processing as a continuous directed transformation. And I think all of those words are very important, and you might say that those words compose into a larger phrase. So the first word is continuous. What does that mean? It means that it's continuing. It means that if there's this question in the back of your head of, is this thing still going on? The answer is always yes. It's also directed. And that's directed in the causality sense. So we say that A implies B here in these states, and that is the direction. It's not that B implies A, that's bidirectional. So we're talking about things that go in one direction, generally the direction of time, and we're talking about the way to transform them. So here's a slide you guys have probably seen before, but we need to talk about it if we're going to talk about distributed systems. So what are concurrent streams? If we're talking about this sort of consistency where one thing happens after another, and we could say that the first state implies the next state, well, what happens if two people both want record 12? Someone's going to have to decide. If it's very important that you only give out that record 12 once, if they both come at the same time, you're going to have to either make one of them wait or give out a duplicate. Neither of those are good options, so what can you do? If this were like a checkout line and there were a bunch of people, you'd just say, well, add a new checkout. So that's exactly what Kafka does with its partitions of its topics. So here we have writes going in concurrently, and there's no problem because they're handled in parallel. What's really interesting about this, and I think hits concurrency on the head, is that we can now no longer say whether records 3 happened in partition 0, 1, or 2 first. There's absolutely no information here that could tell us. And this is what it means to be concurrent. It's two different dimensions of time. Now you can always rebuild it back, right? You could timestamp your data and you can reassemble it, but the concurrency means that there is no logical ordering. Oh, by the way, we've been talking about Kafka. I'm sure you guys already caught this, but we've been talking about Kafka. So Kafka says it's a high throughput log messaging system built for publish and subscribe patterns, but honestly, I think of Kafka more as just a system for distributing concurrent streams. The other part that I want to talk about is reactive programming. Reactive programming is one of these things that's probably said more by business people than programmers, and when the programmers are talking about it, they're usually not talking to each other about the same thing. But I think there's a really simple definition of what this is, and it's just a matter of push versus pull. In our standard systems, we're pulling data out of them. We say, hello, do you have any data for me? And then if they say they do, we extract it from them. Now contrast this to callback-based systems where they push data into you. What you do is you say, here's what I want you to do if anything should ever happen in your system. And then when those things happen, they call your callback. And in this sense, you're forced to react to their events. You don't get the opportunity to not call your callback. Now maybe you want that pull model in some cases specifically for that reason. It's an inversion of control problem. The other thing that goes hand in hand with stream processing is functional programming. And I also define functional programming pretty simply. You're doing functional programming if you're programming with functions. That's it. You don't need to do anything fancy, you just need to program with functions. Now it's a gradient, right? The more functions you're using and the stranger the ways that you use them become, the deeper down that functional labyrinth you're probably going. But in general, just program with functions. So we want to have value expressions, right? We want any expression to be able to be replaced at will with the value that that expression evaluates to, and vice versa. In order to do this, you need something called referential transparency, and in order to do that, you need immutable data, usually. Also, there's this notion of sequence operations. This is the things like map and filter, the things that take what we call higher order functions because they're functions that are defined in terms of functions. Now that thing right there, being defined by something that is like yourself, we call that composition. So if I'm defined in terms of other functions, then I am composed out of functions. So what about Reactive-X? This is one of the libraries that I really want to talk about today. Who here is familiar or who has used Reactive-X? Cool, so almost no one, excellent. So Reactive Extensions came out of Microsoft a few years back, and they're basically a library for working with streams, and specifically for transforming those streams. They describe themselves as a library for composing asynchronous and event-based programs. Now remember what I was saying about composition, how you can define something about yourself based on other inputs that are like you. This is a very interesting property, and we'll get into it a little bit later. First, let's look at the foundation of Reactive Extensions, the observable stream. So the observable stream is just equivalent to an iterable. So with an iterable, you say, oh, can I get an iterator? And when you have that iterator, you can do that data extraction thing. You can say, okay, I'm ready for more data. I'm ready for more data. Now contrast that with the observable, where instead of getting an iterator, you say subscribe. And when you subscribe, you have to project your callbacks into that thing. You say, here's what it means for me to handle a new event. Here's what it means for me to handle the completion. And also, we have to deal with errors because of the inversion of control. But there's some interesting mathematical properties. If you were at this last talk about category theory, you might say that these two things are duals. But the gist of it, at the end of the day, all it really means is that you have these sort of operations that you're used to using, like filter, like select, like scan, like reduce, and you have them available on these data structures that span time. So fold is something that usually should not be able to be done on unbounded lists. And the reason is because fold is this sort of pairwise operation that takes two values and flattens them together all the way down to the end of the list. So what can we do instead if we don't know if the end of the list is ever going to come? What we can do is we can say, okay, 1 goes and that merges into 1. And then 1 and the next state is 3. And then the former state of 3 and the new state merges into 6. And 6 and 4 merges into 10. Now this idea of merging old state and new state is going to be very, very powerful, and we'll look at how it can help us a little bit later. Another, and I think maybe the most powerful idea from Reactive Extensions is this idea of streams as signals. If you think of yourself driving down a street and you think of yourself as a stream processing system, there's all these streams of information, other drivers on the road, what the weather's like today, and you're continuously there processing it. Now remember, you're also traveling through the direction of time, so you fit that model of a stream. So what happens when you see a light change? There's this new thing of information that you haven't been thinking about. It wasn't in the forefront of your mind, and yet when it comes in, you're changing your behavior because you were implicitly defined by this other stream. Now, how does this map into our actual programs? You might think about canceling a request of an AJAX user, right? So you've got a very complicated pipeline that you just triggered, and it's probably going to take a few days to run. And then suddenly the user shows that they're not interested anymore. They say, oh, well, that's not very interesting. And so rather than letting that thing happen, you can actually intersect that stream with this pipeline, and now you can just completely collapse it and not do any more work. So what you're doing here is you're composing streams. And this idea is incredibly powerful. This is the main idea we wanted to use reactive extensions. Some of you are also lucky enough to have seen Martin Klepperman talk about streams in the Unix philosophy. Jade touched on this earlier as well today. The general idea of the Unix philosophy is that you should do one thing and you should do it well, the single responsibility principle. You need to pipe your inputs to your outputs, but it's not just about this pipe operator. That's not where the interesting thing is happening. The interesting thing happens because every program that's in this system programs against a shared abstraction. They all agree that there's this thing called a line, and it's any number of bytes delimited by a new line character, and that if you see that, that shall be your input, and that shall be your output. And because you have this shared abstraction that everyone agrees on, now you can compose your tools together. But it doesn't happen for free. If there wasn't that line, you wouldn't be able to compose. So Kafka becomes like this pipe, but it's still your responsibility to make the shared abstraction in your own domain. So Kafka is a distributed system. I said it was for distributing concurrent streams. So how do we think with distributed streams? There's a whole sort of question, a whole range of questions that you have to ask yourself when you're working in these systems because of the nature of the network. So you might have to ask, did my message get delivered? So the reality we live in is that networks fail, they're asynchronous, and delivery is not guaranteed. So I might say, hello, take my message. And then you say, all right, I'll take that message. And then the next time it comes along, I say, take my message. And then someone cuts my cord. I have a brain aneurysm and I fall down. Now, when I come back, I've got two choices here, right? I can either say, well, I don't know that it was guaranteed that my message was received, or I can say, oh, well, it was probably received and, it's not a big deal anyhow. This is starting to define some delivery semantics. The first one, where you try to deliver it again until you know for sure that it has been received, we call at least once semantics, because we're going to try until it's there at least once. The other one, where you are just really optimistic and say, well, it probably worked, that's called at most once. You sort of start at 0 and work your way towards 1. The other thing that you might have to ask is, have I seen this message before? So if you chose at least once because you knew you needed reliable delivery, now you have to deal with duplicates. So you have to say, have I seen this message before? The other thing that you have to deal with is message reordering. So if you're in 3 different states and you're all simultaneously trying to send an event, well, the geographic distance alone is going to make those happen in a different order or be received in a different order. And geographic location isn't the only thing that's going to cause data skew. You can also have internal latency. You have GC pauses. So you have to ask yourself, are these the order that I intend them to be in? Finally, you might ask, have I seen this before? So how do we deal with these problems? These problems are very, very challenging and not something that we usually deal with as regular application developers. But they're very old problems, and they've been around forever because they're so fundamental. The first tool that we have, and the one that we're probably the most familiar with, is this causal consistency, this idea that one thing happens before another. And again, this is directionality. We say that it was in state 1, and then after that, it was in state B. There's no in-between about this. There's no ambiguity, right? It happens, and that's the end of the story. But it's not just enough that there's causal consistency, that you know that this thing implies this other thing. The other thing that you need is atomic broadcast. If you're in a distributed environment, it's important that everyone sees that update at the same time. You can get this, for example, by using Zookeeper. I recommend you do. The problem with causal consistency and sequential consistency is that it's the most expensive of all. So what happens if you need this sort of reliability, but you can't afford to pay the synchronization costs? Well, there's also another tool out there available to us programmers called eventual consistency. And I think when eventual consistency first came out, people thought about it as a maybe consistency, probably not really consistency or kind of. But actually, some very smart people, Mark Shapiro and friends, have demonstrated that there's this interesting property you can get where so long as everyone receives the same set of operations, everyone will be in the same resulting end state. So here we have 3 nodes. We have nodes x1, x2, and x3. And they're doing 2 concurrent operations. We don't know which happened first, but again, they're concurrent, so it doesn't matter. What does matter is that those operations propagate out to the other servers. And in fact, every operation must propagate out to every other server. Now, there are a lot of ways you can do this. You can use gossip protocols, but it's generally a solved problem. Now, if you were paying attention to that last slide, you might have seen that all of the magic was happening inside of this merge function. That there's this interesting property, and these things are called CRDTS, which is commutative or convergent replicated data types. And these things are made specifically for a distributed environment, specifically to be run in parallel. And all you need to do is you need to be able to take 2 states, states A and B, and you need to be able to merge them into new state C. It's important that when you do that merge operation, that it is bigger than states A and B, in the causality sense is bigger, right? That it is the new state of the system and not a former state of the system, because that would violate the principles. And also because of the way the network works, because you might receive these messages more than once, because you might receive them out of order, you also need to guarantee a few mathematical properties. You need to ensure that your merge function is commutative. And what that means is that I can take this new and this old, and I can swap them around, and it won't change the behavior of the function. There's also this property called associativity, and that means that I can flip these applications to merge, and it's no different than had I not done that. Finally, it needs to be idempotent, which means that if I call the thing once versus calling it many times, there's no difference. An example of an idempotent operation is like setting x to 1. No matter how many times you say set x to 1, the end result is going to be 1 in that database. So hopefully you can see why these mathematical properties actually link directly back to the nature of the distributed networks that we're working on. Now that we kind of understand the way that all of these things work, we can start to talk about the different models, the different techniques that people are using. The most popular are the continuous operator models, the 1 record at a time style, and the micro-batch models, the many records at a time style. A lot of people coming from functional programming are going to prefer the micro-batch because list operations are their bread and butter, and anything that can make it more listy is something that they're going to go after. The other people really like 1 record at a time because it's like these little propagator networks. It's like these little nodes in a graph, and you can control them independently and discretely. You'll have some other options. Do you want to use local state and just have everyone have a local cache of the data, or do you want to distribute out your state? Again, these are the decisions that you're going to have to make based on performance, based on what makes sense for how you're going to use it. When you run your stream processing job, is it going to be deterministic? Is it going to do exactly the same thing every single time you run it? Or can you afford non-determinism? Can it be observably deterministic? Is your data set bounded, something that's known to end like a web session, or is it unbounded? Is it something that's never going to end like the procession of the seasons? And do you need to, when you're like merging your data into your result set, does that need to be synchronous? Can no one else do that at the same time? Or can you afford it to be uncoordinated? So you might be kind of confused here saying, well, this is a lot of stuff. This is kind of like a paradox of choice, and which way should I use? Honestly, there's no silver bullet, and like everything else, I'm not going to be able to give you one answer, but use your head and look at the problems and see what guarantees you need to be able to apply. Often you'll need some combination of both. Often you'll need strong consistency and eventual consistency. Often you'll need local cache state and distributed state. What I can tell you is regardless of what you choose, your solutions need to compose. You need to be able to take one solution and put it into another, and that should stack all the way up. And finally, different systems have different requirements. So if I can't tell you what model is right for you without talking more, what can we do instead? I think if you form values and you use them to guide your decisions, that you can generally wind up in a pretty good place. So what I'm going to say is you should look for things that let you program against value transformations, things that let you push the integration to the edges. So if I'm going to make a very complicated system, I don't want the internals of some dependent system leaking into the implementation. I want to program against simple abstractions, and I want to make sure that I treat things separately. Again, this is just applying the Unix principles. So finally, what does this library look like? What does it do? So here's a simple consumer, and what we do here is we connect to Zookeeper, much like the high-level Kafka consumer does, and then we say, get me a message stream for a particular topic. Of course, we support the whitelist, wildcards, and everything. We're always just delegating to Kafka underneath. It's very important that we don't try to go in a different direction, but instead we just become a faithful model on top of Kafka itself. Here we tumble 5 seconds, so we split it into 5-second windows, so we just here in process decided I would prefer microbatch for this problem. Now, I could have done something else. I could have done map, and then I would have been a little bit closer to the continuous operator model. And then finally, I'm able to just process it whatever makes sense for me. I also said that it's important to program against value transformations, and the reason is that if your systems are going to live a long time, they're going to change a lot. And you need to be able to define things that won't change. You need to be able to say that no matter what happens in this system, it should always be true that when I poke it this way, this thing happens. So here, because we've pushed our integration to the edges, because we don't even take it, we program our consumers to where they don't even know anything about Kafka. What they know about is a stream of values. And so then we fake out that stream of values in process. Kafka's producers are behind an interface, so we can fake that out in process as well. So we completely have arbitrary transformations, and it's all at the level of data. So the important thing I want to get across is that if you're around for a long, long time, the systems that you're working with are going to come and go. It doesn't matter where your data is loaded from. It doesn't matter if it's coming in over batch, if it's streamed in from mobile sensors, if it's typed in by monkeys at a computer. The only thing that matters is how you're going to process it. It doesn't matter where it's stored. The only thing that matters is the abstraction you're going to use when you talk about it. So how about distribution? We've been talking about distributed systems. We've been talking about concurrency. How does this thing distribute? And we also kind of sidestepped this problem. We said, well, Kafka naturally distributes horizontally. It's distributed by default. And so does this thing run on Mesos? Does it run on Yarn, Docker, or AWS, or your new cloud of choice? The answer is that that's an application concern. And we're not going to be able to map that faithfully for you. You're going to have to make the decision of how you want to scale your consumers when that time comes. Our only job is to step back and make sure that you're able to make that decision. So you can run on 1 server or 100. And in fact, if you're programming these things right, it shouldn't matter if you only have 10 events a day or 100 billion events per day. You should be able to decide the boundaries of your program. So you might say, oh, well, that's all well and good, but I just need a framework that gives me exactly once processing. I don't care how it does it, I just need it. And to that I'll say, well, do you really? Maybe we should have a conversation. Let's talk about what exactly once means for you. I can tell you all kinds of reasons why you probably won't want it, but rather than doing that, I'm going to talk about how we enable it. So here we have a stream, and honestly, it doesn't matter what this stream is. All we're doing is we're processing it as a bucket, and then we're committing. And that commit here takes a merge callback. And what that merge callback is going to do is take the offsets that are global, the ones that are distributed and shared, and the ones that you're proposing. And then it's going to give them to your program and give you the opportunity to reconcile. So what might happen is there might be work that was unaccounted for. Someone might have done that thing where they processed the data and then crashed before they were able to acknowledge it. Now this is known, it's at least one, so we're going to process it again. But maybe there's some weird side effect in our processing that we really can't accommodate. Maybe we actually need to detect this sort of thing happening, and we need to unwind or unprocess data. Now this isn't idempotent by, in the mathematical sense, but it is observably idempotent. This commit also happens in the context of a zookeeper lock. So this commit is synchronous across the consumer group. So there's this thing here, and it's very, very complex and needs to be used in a very specific way, but is very powerful. What you should do first is you should just accept idempotency. Just learn to live and love it. But if you can't, there are other ways around it. We can use the things we learned from eventual consistency. We can apply those operations to what it means to add our thing into our result set. All right, so let's try to do a little demo. Always the best part. So that tweet code that I was showing at the beginning was actually real code. More or less. So here we're using the Twitter for J library, and of course it just gives you callbacks when things happen, but you can query tweet streams, and so what we do is we transform that callback API into a streaming API. And then when we have this observable, we're able to group it by the topic that it needs to belong in. When we found that, we're just going to take these substreams and put them into producer records. And when they're producer records, then we can call this save to Kafka method. When that happens, we're going to map the results of this message being saved into Kafka into a log message. And here, we can take our producer stream in process and our consumer stream in process and just use the for comprehension in Scala to get one stream out of it. And that's here, producer.merge consumer. So what happens if we run something like this? So again, the maybe, if I'm lucky. I think I might be having some cool network issues with my Kafka cluster. Crying. Oh yeah, starting Kafka is always a good idea. Cool. And now that it's up, we can see these log messages streaming out. So what's happened is we just mapped a simple callback API into an observable stream. And I'll show you guys how that's done. So this Twitter for J library just is pretty simple. You have to implement this status listener like most callback sort of classes, and you're given an onNext handler. Well, here we're just using a publish subject, which is something kind of like a promise in Rx, and you just get to push events into it, and then the other things can read the events out. And what's really nice is that when we read messages out of Kafka, we kind of marshal them into this committable context of a message. And then when we save them in, we're able to use that exact same message because there's this abstraction that's just a message that is persisted inside of Kafka. And it doesn't matter whether it comes from the producer or the consumer. It really is just a thing with offsets and a location in Kafka. So here, we're demonstrating being able to use your own form of concurrency. This could easily be actors. It could easily be any other method that makes sense in your system. Yeah, so that's kind of the demo part. So why do I think that this stuff is important? Why do I think this is all a really good idea? I think some of the highest things that you can aim for is this idea of natural design. I think that the best designs have already been invented by nature. They've been hardened over millions and millions of years. I think that when object-oriented programming came out, it kind of touched on something like that. It mapped into our mental model. Maybe it didn't map into reality, but it was something that was familiar to us. Now, I think these streams, however, are much more natural and much more familiar to our everyday operation. And we might not be thinking of it like this. We might not be thinking of these transformations so concretely, but I really do think that streams are a natural model to our world. So Donald A. Norman said, good designs fit our needs so well that the design is invisible. I think when the best thing happens, you don't even know if anything happened at all. An example is a doorknob. It's so natural to use that it doesn't feel designed. You just sit there and you twist it. That's how programming should be. The other important idea is that streams are just lists plus this notion of time. The abstractions need to compose onto one another. And here I think that they do. You have this abstraction of a list, and you have this abstraction of time, and then you can try to plus them together to make a new abstraction. I think that Kafka is a beautiful abstraction for distributing streams, and I think that Reactive Extensions is a marvelous abstraction for transforming those streams. I think we need to change how our programs work so we're pushing more unbounded lists in and out. Finally, I think that this is really important because our tools are going to shape how we think. If we're working in a DSL and that DSL is sadistic, we're going to start thinking that way. If we're thinking about state mutations, we're going to start thinking that way. So we don't need tools to make things easy for us. We need tools to help us think clearly. And finally, we need to protect our ability to change. We need to not be locked into our solutions. We need to be programming against abstractions. So there's this wonderful quote by Henrik Nygård from Spotify, and he says, "System architecture should support the addition of any feature at any time." This might sound kind of weird because why would you want to, for example, add MP3s in the middle of your data pipeline? Well, the answer is the problems change in ways that you cannot predict. And so you have to be willing to accommodate this style of thinking. Finally, what do we plan for the future for this library? Well, with the changes in Kafka and the shift from Scala to Java, we're going to port this thing to Java. We don't plan on changing our consumers. We still want to use Scala, but we're going to make that a thin layer over the Java underbelly. There's a little work to do as far as API cleanup goes. There's some types that we think are kind of incidental that we'd like to erase. And we would like an out-of-the-box Mesos or yarn layer for the consumers. I think what would be best of all is if we could see these things like Rx and Curator inside of Kafka core instead of something that only the community is doing on the side. With that, that's all I got. So thank you, everyone. And if anyone has any questions, I'd be glad to answer them.